So since we have identified that what are the major services, we have also identified the relationships between them, that how they talk to each other. We have also chosen the database. We have also found out these APIs and schemas in our system, right? So now it's the right time that we talk about the scaling requirements of our system, right? So this is from the previous slide where we identified that we will need 40 petabyte for storing all the photos in 6 years. Now let's see the requirements, space requirements for metadata. So if this looks daunting and difficult to you, then I'm sure you have not taken the doing quick and fast approximate calculations class, which is a prerequisite. So I won't be going into the detail on this slide, because if you attend that class, then this is a piece of cake for you, right? And in that class, I specifically talked about this photo sharing use case. So space required for metadata. So for user table, we will need 50 GB. For photo table, we will need 70 TB. For user follows table, we will need 4 TB. For user photo table, we will need 100 TB. So all in all, we will need approximately 175 TB for metadata. For 6 years. Okay. And definitely one commodity server will not be able to hold 175 terabyte of data. So we need to shard data. So we will discuss shard again. We will discuss shard in next slides. Okay, so we have identified the need for sharding, and we have identified a need that our system is going to hit bottlenecks in terms of storage and other criteria, right? So there was a previous question on identifying weak backend knowledge and strong backend knowledge, right? So this is the part where I would say that most of the calls or most of the gut feeling can be made from an interviewer. If you are efficiently and expertly talking about finding bottlenecks in your system proactively, then it shows that you have a good knowledge about backend. And even for experienced engineers, given the stress of an interview environment, this could be a difficult problem. That how do you structure your thought process and spot all the bottlenecks in the system. And personally, I have taken many system design interviews, and I have seen many candidates faltering in this time, or they just become frozen when I explicitly ask them to identify bottlenecks in the system. So what I propose is that we follow a template for this. And with this template, we can dissect through our high-level design, and we can propose smart solutions for bottlenecks. I'm very excited about this slide, so please pay attention to it. Identify bottlenecks, and for this I have an acronym SDPHAG, and if you want to remember it, at storekeeper, through, pizza, hamburger, and gravy. So storekeeper means storage, through means throughput, pizza, parallelism, hamburgers are always hot, so it is a hotspot, and availability, and gravy is for geo. Right. So in fact, when you are done with the high level design and identifying the database schema, then you can, instead of your interviewer poking you, you can just go ahead and say, okay, interviewer, please let me find the bottlenecks in my design now. Let me poke holes in my own design now. Right? And then you can say that, okay, these are the 6 areas on which I'm going to do a deep dive on the bottlenecks. Right. So first of all, storage. So again, storage, there are 2 layers of storage. One is for photos and another one is for metadata. So first for photos. So we established that we need 40 petabytes for 6 years. And of course, this data requirement would only grow as our service grows in popularity. And this much data cannot exist on one server. That's quite natural. So that's why we need to have a distributed file storage, right? So when distributed file storage is there, that means we need to have some kind of everyone's favorite word, sharding. Right. Let's say we need n servers for storing all our photos. Okay. Then what we can do is that we can come up with a strategy that photo ID mod n. So every photo goes to a server ID, which is photo ID mod n. Right. So that means we are sharding on photo ID here. So if you want to understand it more, let's say this is one server where you are storing all your photos. Okay, you are storing all your photos. These all are your photos. So each row is a photo, let's say. Now there comes the time when all these rows are filled now, right? So that means the storage is filled on this server. So that means you have hit the limit of vertical scaling, right? So now you were trying to scale it vertically, where you were just increasing the disk size, and now there has come a time when you have hit the limit of vertical scaling. So what you do horizontal scaling. And so instead of y-axis, you go on x-axis now. And how you can do that? By adding more servers here. So let's say you add another server. So when you add another server, so what you would do is that you would take half of the photos from this server and you will move them to this server. So right, so now they both are storing the photos. So some photos are here and some photos are here. And how did we do that? We did that by sharding horizontally. Right? So you have heard about horizontal sharding and vertical sharding. Right? So what we did was that we said that this is my cutoff point. Right? So all the photos below this cutoff point remain on this server, and all the photos above this cutoff point are moved to the another server. So we have made a cut. So shards are actually cuts, right? Small pieces. So we have done a cut. We have done sharding horizontally here. Again, there will come a time when these servers will also get full. Right? So again, we will do horizontal scaling. We will add more servers here. Right? So again, we will be doing horizontal sharding on these two and moving the load to these two new servers. Sorry about the background knocking noise. There's some construction work going on. Cannot help it. Or maybe let me put on my headphones. That will reduce the noise. Okay. Can you hear me with the headphones? Please type yes in the chat box. Okay, thank you. I hope that reduces some noise. Can't help it. I'm sorry. Right. So this is how we were discussing the sharding, and now you have these 4 servers here, right? So that means n is equal to 4. Now whenever a photo has to be stored, we do a photo ID mod n, and we send that photo on a specific server. And by the functionalities given in these databases, or even if you are making these databases from ground up, you need to have replica for each server. So what you will do is that you will have a replica for each server, replica for each server, replica for each server. Okay, so this is how we address the storage bottleneck for photos by doing sharding, and then we also discussed that how we are going to do the sharding, and we also touched a bit on the fundamentals of doing sharding. Just curious, is the knocking sound a bit less now? Sorry. I purchased these noise cancellation headphones. They're expensive ones. I'm not sure they're still not working properly. Yeah, time to buy some new noise cancellation headphones. Yeah, please do let me know if you have any suggestions for any good quality noise cancellation headphones. Thank you. Separation of read and write when you say replica. No, Srinivasan. So I'll explain it very briefly, Srinivasan, because I have explained this replication thing in detail in how to choose database, a prerequisite video. So please do watch that. So what is replication? So let's say this is one server, right, where you have some Justin Bieber's nice selfie. Now, let's say you store this selfie on only one server. Let's say this server is one, and then some lightning strikes, maybe from Thor, and this server goes boom. Okay, this server is destroyed. So what will happen? That this selfie of Justin Bieber is lost forever, and you don't want to upset customers like Justin Bieber. So what you should do? What you should do is that as soon as that first selfie is stored on this S1 server, you should make copies. You should make copies on another replica servers. Let's say this is replica 1, this is replica 2. So that Justin Bieber's selfies are always preserved. Right, so this gives us reliability. We talked about reliability being an important aspect. Right? And then you can go a further step ahead also in replication. That what you can do is that you can put these replicas in different geolocations. So you can put this replica in North America, you can put these replicas. So you can have multiple replicas here in EU, then you can have another in Asia, you can have another multiple replicas here. So even if some natural calamity happens in one of the region, then also the other two geolocations are always available. And there is another beautiful disaster recovery. And then there is another beautiful use case for these replicas, that you can have multiple read requests powered by all these replicas. Right? So the more replicas you have, the more read requests you can serve. Right? So this is, again, you are horizontally scaling your replicas. And another thing, that based on a user's location, you can choose a replica. So if my user is from North America, they can go to all the replicas in North America. If user is from EU, they can go to all the replicas in EU. So that means serving the request from the nearest servers, nearest replicas. Okay, so let's move to storage bottleneck for metadata. Remember, we are identifying the bottlenecks in our system proactively. So now, how would you do it? Just a thought exercise again. So when you say that, okay, Mr. Interviewer or Miss Interviewer, I want to identify the bottlenecks in my design. So you will open the design in your front, and then storekeeper through pizza, hamburger, and gravy. You know this, so you will see as storage. So you will see, okay, so storage bottleneck is on all the databases, right? So you know that there are two databases here, two data storage layers here. So we are doing that. So we are identifying the bottleneck on these two storage layers. So now storage bottleneck for metadata. So as per our calculation, we have seen that 175 TB data is required for 6 years. Again, one server is not enough, right? So we know that there will be one server. Let's say this server's capacity is 4 terabyte. So we keep on filling it. And there comes a day when vertical scaling is not an option anymore. So we decide that we are going to horizontally sharded, right? Now we have to decide. So we have to decide that this sharding is done on what basis, right? So what are the things that we are storing here? Right? We are storing user information. We are storing photo information. These are the two primary informations that we are storing. So let's brainstorm sharding strategy on them. First one is, let's say we shard on user ID. Okay, so this sounds like a good idea, right? That what can happen is that there is this one server where, let's say we have only 100 users, for example. So user 1 to user 50, they all go here. User 51 to user 100, they all go here. Okay, sounds good. We have good balance of load. We will always do mod n on a request, this user ID mod n, and we'll find a specific server. Yeah, simple solution. But what happens if our favorite Mr. Justin Bieber is a user on this server? So there was a question also related to this, that how we will handle this celebrity scenario. So this is that point here, right? So for hot users who post a lot of photos, and for celebrities who are followed by millions of users, this particular shard would be accessed manifold times. Okay, so this particular shard will become a hotspot. So this poor shard will have millions of requests, and this one will have only few requests, right? So of course this will be bombarded, and this server will not be able to bear the load of so many requests, of millions of requests. So what do we do? So we have another option, sharding on photo ID, right? So when the request comes for storing a photo, upload service would contact ID generation service to request a photo ID. So this we have already discussed, right? Then it would save the photo on cold storage and save the information of metadata shard using this strategy. So what will happen is that, let's say we have 3 shards, S1, S2, S3. So some photos are going here, some photos are going here, and some photos are going here, okay, based on mod n strategy. And then you can also say that, okay, what if the selfie of Justin Bieber is on this shard? Right. Then this server is going to be, the server is going to bear the brunt of the millions of crazy fans. So in those cases, this is a throughput bottleneck. You understand throughput, right? The number of requests that are coming. So this is a throughput bottleneck, and that is the next step of our strategy, right? So we will address that. Now, just another interesting exercise, that with sharding, how many metadata servers will be required? So we said that 175 TB of data is there, and we can say that 1 TB shard is 4 TB. We can say that one server can store up to 4 TB. Again, I'll I'll explain it at a very shallow level because this is covered in great details in previous video, which are in prerequisites. So dividing 175 by 4, right? So that is 44. So we need 44 shards, and generally database servers are filled up to 70% capacity. So that means we need to have 63 shards, that means servers. And we talked about the replica in previous slide, that how we should have more replicas. So if we want to have 2 more replicas, that means our replication factor becomes 3. So that means we need to have 189 servers. Yeah, thank you, Sri, for asking that question. Good question. So yeah, Gurvi. So in my prerequisite, I mentioned 100 TB here. Okay, yeah. So sorry about that. Actually, I prepared these slides much earlier, before that prerequisite. So when I did more research, then I identified that okay, 100 TB is also a fair number to be assumed. So that's why I have 4 TB here and 100 TB there. So I'll improve the slides here, but you can take the reference numbers from that prerequisite video. Thank you for asking that. Yeah, coming back to 175 TB is for photos, for metadata. It's here, right? Storage bottleneck for metadata. We are discussing here, so it's 175 TB. For photos, we already discussed here that it is 40 petabyte. And yeah, coming back to Sri's question. This is a very interesting question, Sri. Let me take a moment to let's brainstorm it. Okay. So let's say we are sharding on photo ID. So sorry, on user ID. User ID. So in that case, what will happen is, let's say all Justin Bieber's photos are here, or all Selena Gomez photos are here, all Leonardo DiCaprio photos are here, right? By some weird luck, and all the simple users are here. Now, in this case, what will happen is that we need to cache all the photos from Justin Bieber, or we need to cache all the photos from Leonardo, or all the photos from Selena Gomez. Right? Whereas if we shard by photo ID, just a second, batteries. Whereas if we shard by photo ID, in that case, we know that not all Justin Bieber's photos are famous, not all Selena Gomez's photos are famous, right? And we can be pretty confident that when we talk about photo ID, they would be, again, we cannot say it with 100% confidence, but probability is higher that they will be distributed in a more equal fashion. So in that case, it becomes much more efficient way to put a cache before a server. For only the photos which are popular. So let's say on this server only 1000 photos are famous. So all those 1000 photos are put on a cache server. So if we brainstorm on both these designs, this one makes more sense. This one gives us more flexibility in terms of caching compared to this one. Okay, so let's talk about the throughput bottleneck for services. Right. So again, you will open the diagram that you have created, and you will identify all the microservices, and then you will pick them one by one and brainstorm that what kind of throughput bottleneck you can have. So we have upload service and download service. Right. So again, so we would have multiple servers running behind the load balancers. And these points, right, even if this sound common sense to everyone, right, it's very important to spell them out verbally and specifically during the interview. Right, please do that. Please tell the interviewer specifically that I will be running multiple servers for this microservice, and they will be running behind a load balancer. Then you can mention that what kind of load balancing strategy you can have. Right, so it's safe to say that in most of the cases, generic cases, round robin is a valid algorithm, and you can also go for least connection and least load kind of approaches. Right. So once you mention that, then you can say that I'll be running all my servers at 40 to 50% capacity of CPU. In case your service is CPU bound, and most of the services are CPU bound. So even if your traffic, the number of requests becomes 2x suddenly, then also you can handle that load. Then you address the next point. What if the requests become more than 2 times suddenly? In that case, you need to have auto scaling. Right? And those auto scaling could be triggered that when CPU crosses a threshold like more than 60% for 5 minutes, or requests per second increase by more than 2x for 5 minutes. Right? In that case, you can have auto scaling so that your service is scaled horizontally automatically. Then you can go on and display your backend skills more, and you can tell them that we have a load balancer and new servers are being added automatically. Right? So we will have service discovery in place, and if you do not understand what is service discovery, then this is the actually I'm not I should have done, I'm not sure that the service discovery is explained by Omkar in fundamentals or not. But it's a very simple concept that what happens is that if there is a load balancer and then there are servers behind that load balancer. Right? So let's say you have only 2 servers, and by auto scaling, 2 new servers are added, S3 and S4. So there should be a mechanism by which load balancer understands that these S3 and S4 servers are also in a good condition. They are also that these servers are in a good condition. They are in a healthy condition to accept requests, right? So what happens is that these servers, they register, uh, and then load balancer does some health checks on them, like TCP health checks. So TCP health check is simple ping. So TCP load balancer will send a ping and they will reply a pong. So simple TCP handshake is there. So the load balancer understands that okay, these two servers are at least operational. Then it will like to identify that if the service microservice is running or not. In that case, load balancer will hit a health check API on this particular S3 and S4. So that health check is done, and if they reply okay for that health check, then load balancer understands okay, these two new servers are operational and they can also serve requests. So now this will become just one big cluster where all servers are getting the requests in equal proportion. Right. So this is service discovery. Of course, like I have explained this service discovery at a very shallow level, but this is almost the detail you need to know. But it's a good thing to understand about service discovery. So please do spend some 20-30 minutes in understanding it. So Asim, see, if we have to make our system scalable, right? If we have to design Instagram, or if you have to design Twitter-like system, which are horizontally scalable, then these systems are the fundamentals, right? These things are the fundamentals. That how load balancer comes into the play, how these servers are running behind the load balancer, how servers are automatically added in load balancer. The whole expectation of the system design interview is testing distributed systems knowledge, right? Because if distributed system doesn't come into the picture, then world is very easy. Like imagine a world before Google in 2000, where you could just create one big Oracle database and 2,000, 3,000 users could be served from that server. Now, if you need more users, you add more capacity to that particular server. You vertically scale it. Right? But after Google, there are millions of users who are making concurrent requests. So in those scenarios, distributed systems is the only solution. Okay, so for throughput, we have discussed throughput bottleneck for services. Yeah, throughput bottleneck for storage servers. Because the storage servers also have to serve the request, right? So like the metadata database and the cold storage database. So again, in terms of CPU, our systems are running at 40% capacity, and we are sharding enabled, right? We have multiple replicas running. So whenever the number of requests coming to those servers increase beyond a limit, we can always add new replicas. Okay. Now let's consider the caching aspect. Right. So our system is read heavy. Right. We have seen that reads are thousands or 10,000 times of writes. Right. So in this case, what we can do is that we can have a caching layer. Right. So what you can do is that you go back to the diagram, right? Let me erase these things. Just resolve it here. So now you go and see, okay, so where I can introduce the caching layer. Okay, so one thing is surely that you can have a caching layer here before the metadata database, right? Now what kind of caching you can have here? So first of all, you generally you cache the most recently and frequently accessed entries in the cache, right? Yeah, green is more visible than yellow. Okay, so you have a caching layer here. So what you do is that, and you cannot put everything in cache. That's the whole purpose of having cache, that the requests which are getting the most number of hits or which are hit the most recently, they should be put in cache. So that's why we have least recently used, LRU, LFU, least frequently used kind of caches, and we have very advanced generational level type of things also for caching, but that's out of the scope right now. So yeah, so the basic thing is that what you should put in cache, right? So you should put some kind of top n entries into cache, right? And then this cache has to be a key value kind of cache, where the user gives a query based on the key and you simply return the value. And this value could be a collection of multiple columns, right? And you can have caching solutions like Redis. You can have solutions like memcached. So this part also I've discussed very in great details in the choosing database prerequisite video. So please refer to that. But that's why I'm using the Redis and memcached words here directly. So I've explained in that video. Yeah. So you identify that, okay, Redis, memcached, these kind of caching solutions you can have. Again, before the object storage also, you can have caching solution here. You can have another caching layer here. Right. Okay, I'm taking a pause here. Any questions on caching? And let me check the questions also. For general guidance, cache storage. Yes, I. So that actually that I have already explained in the prerequisite video. So and I've explained on this slide also. Okay, I didn't talk about. So going by the 80-20 principle, generally what we do is that we cache 20% of data in memory, and this 20% data means the data based on LRU and LFU, and this should suffice for serving our 80% of requests. And I've seen personally that the offset is even higher, like 80-20 can go to actually 90 and 10 also. That 10% of data is serving all the 90% requests. And then another good advantage of the caching is that what you're doing is that you're reducing the calls to, that was the whole purpose, right? So we are addressing the throughput, right? So once you have put the cache layer here, the 80% of request will be served from this cache itself, and only 20% of requests are going to this metadata database. Similarly, here also in object storage, only 20% requests are going. Right? So this is how caching is helping us to solve the throughput problem, throughput bottleneck. This would help in handling the throughput and helping our system to be available. For storage, shouldn't throughput be based on I/O rather than CPU? Also, shouldn't scaling be based on storage? So scaling based on storage, we have already covered, Abhirit, when we talked about the first bottleneck on storage, and we came with the sharding solution. Now we have addressed that, and now we have come to the throughput problem. Right, I'm talking about scaling out. Didn't get you. Scaling out means? I'll wait for a response. Let me take another question still. If we shared using photo ID, if we shred using photo ID, isn't going to be a problem for download service, since it has to be scattered together. We'll add more latency and load on download service. There is a comment. Yeah, sure. Yeah, so it's a good question, Amay. So we can think about it more. Generally, you wouldn't have these kind of requests that give me all the photos of a particular user, right? Let's say if a user has 1000 photos spread on 100 multiple servers. So it's you don't have such kind of use case that you will say that, okay, give me all the 1000 photos for that user, and that scatter and gather happens in that case, right? So it is not a feasible use case. It doesn't happen. What generally happens is that you make that calls page by page. You see the first 50 photos, then you see the next 50 photos, then the next 50 photos. And in that cases, you can always write your code in such a way that those paginated 50 photos that you are fetching, they are done from the same server. That once you have exhausted all that particular server, then you go to the next server. Even if scatter and gather happens, and yes, there could be a freak scenario there where a user has only 50 photos and all those 50 photos are on different shards. That is a case possibly. So in those cases, yes, those users are not very active users, right? And in those cases, you will take that hit. you Yeah, so download photo by user ID. So again, in this case, again caching. You will have caching based solutions in this, right? So let's say if it is a celebrity user, then you will have their photos in a cache, so that this API is served from the cache itself. Let's say somehow every after this session, 50 people start seeing my photos on Instagram. I'm not on Instagram, but still. So in that case, also the system will identify that after one or two requests, system will identify, okay, so many people are trying to see Rajyavardhan's photos. So in that case, again, we will have some kind of LRU cache kicking in, and my photos will be put in a cache so that the next set of requests are served from the cache itself. So for the 100% of the requests, we can never provide any kind of guarantees. Right? So that's why we have 90 percentile, 95 percentile, 99 percentile, or maximum 99.9 percentile metrics. But we can never have 100 percentile metrics to ensure performance. I hope that answers your question. Yes. Storage having multiple. Awesome. Abhi has posted. If you go back 2 slides where you were doing storage, after you mentioned we can have storage at 40% in that case. That was for CPU capacity. This one, right? Our servers are running at 40% capacity. Yeah, this is CPU because we're talking about throughput. Or it could be as someone, okay, you only, yes, yeah, so it could be based on CPU or it could be based on IO also, whatever is the bottleneck. So yes, so you can say that. I'll update my slides for this. Thank you for pointing out. So I'll explicitly mention that in case of storage server, it could be CPU or it could be IO. Yes. If you scale storage having multiple replication cells, how do you handle the shards? What do you mean that? How do you handle the shards if you scale storage? So that is how sharding works, right? So you divide the data in shards, and for each shard you have replication servers, and they are constantly being updated by the primary shard. Not sure, Gustavo. Maybe you can explain it more. Oh, we got it. Thank you. Okay, so we are at P part now. Parallelism. Right. This comes into picture if there are some bulky requests being made to the system. So what parallelism means that if the same request can be broken down in such a way that it is served by multiple servers or multiple threads concurrently. Now in our use case, we have simple photos, right, which are being uploaded or downloaded. We do not have bulky APIs, bulky requests, right? If somebody is saying that I want to download some huge data, or if I want to upload huge data, download or upload huge data. In those cases, bulky requests would come into the picture, right? So in our case, we are okay that user opens a single connection to our services, right? And works on that. So parallelism wouldn't be a bottleneck in this one. Hotspots, right? So what are hotspots? That if a particular single server is bombarded by the request, right? So there are two things here. So one is the sharding strategy, right? So by sharding strategy, we ensure that the particular celebrity photos are not on one server. And second is caching is also help us to solve the hotspots here, right? Because as soon as one server starts getting multiple requests for the similar request, that data is upgraded to cache, and these requests start getting served from the cache, right? So caching also helps us to solve hotspot bottlenecks. Then we talk about the availability, that our system should be highly available and should be able to serve the requests. So for services, right, the compute part, we have already seen that we have load balancers and multiple servers are running behind that. So this will ensure the high availability. And of course, those servers will be stateless, so that horizontally they are scalable easily. And similarly, sharding and replication, they also make our system highly available, right? Because let's say this is again selfie of Justin Bieber, and then we have replicas here, right? Which also has the selfie. So the requests can go to these servers also for getting Justin Bieber selfie, and here also. So by having multiple replicas, we are making our system available also. So even if this goes down, still we have these two. Okay, we come to the last bottleneck of the acronym, geo. So if our servers and storage are located only in one region, let's say North America, right? Then the request coming from Asia would have very high latency. So if this is North America, and these are, let me use a different color. These are users in Asia. So the requests are coming here. It's from Asia to North America. So this intercontinental across the globe latency could be as high as 400 to 500 milliseconds. Right? And the users in North America, for them, this will be acceptable. For them, it will be, let's say, 50 to 100 milliseconds. But for these poor people in Asia, they will have 500 milliseconds latency. Right? Now, how do we solve this problem? So that's where the geolocation. So this is the geolocation bottleneck. Right? First of all, this is the geolocation bottleneck. Now, of course, the users in Asia, they have to get low latency, right? And similarly for the folks in EU also, right? So unfortunately, they are also getting some kind of maybe 200 to 300 millisecond latency somewhere in the middle. So how do we balance it? So there are two ideas. Idea number one, we have our servers and database instances in multiple regions spread across the world. Then using DNS policy, we make sure that a request is directed to the nearest server. What does it mean? It means that this red square that we have, this is our infra stack, right? This is our infra stack. So we should replicate it in other geolocations. So basically I should have a infra stack here as well. I should have an infra stack here as well. And now when the request comes from a user in Asia, so that request goes to a DNS server first, right? So the DNS server is smart enough to identify that which is the nearest server. So it will identify, okay, so the nearest servers are here. So request will stop going here and they will start coming to this infra stack here. Similarly for EU users, it will happen. Or let's say if there is no stack in EU, then if we see the EU is like this, right? So what will happen is that the West Europe request will be going to North America and East Europe request will be going to the Asia layer. Right, so this is the first idea. Second idea is to use CDN. Right, so this is simple, that we will have geo-specific CDNs. Okay, and so in this case, sudden burst of millions of requests would be efficiently served by region-specific CDN servers. Okay, so it will be a very simple scenario that there will be a CDN in NA, there will be a CDN in EU, there will be a CDN in Asia, and a lot of cache is populated in these CDNs. So most of the requests from Asia, they will be served here, requests from EU will be served here, requests from NA will be served here. And CDNs are expensive. CDNs are expensive. So you wouldn't throw everything inside CDNs. Similar to you wouldn't throw everything into a in-memory cache. Okay, so geo bottleneck also we have discussed. Okay, so we are at the end. We've discussed everything. Let me go through the questions. What are the example of bulky request system? Bulky requests are where you are uploading or downloading something which is very heavy. Let's say you are downloading a 1 gigabyte video from your Google Drive. Right? So in that case, those are so let's say there is a 1 gigabyte file, right? So actually it will be, let's say it is served as multiple chunks. It will be served as multiple chunks, your 1 gigabyte file. So when the client says that I want to download it, right? So what happens is that the multiple parallel requests can be opened, and these chunks are sent to the client in parallel threads, and then client can collect all those chunks and it can tie them together to make the 1 GB file. And similarly in upload also the reverse scenario, that these chunks are sent to the backend in multiple threads. So this is one bulky request. Another bulky request are related to analytics. So where let's say you are trying to find the trending hashtags in last 7 days from all tweets. Imagine the kind of data for all the tweets in 7 days, and then you have to find the top trending hashtags from that. So in this case, you have to parallelize the operation. Right? The multiple hundreds of threads are running in sync. Not sync, they are running concurrently and going through the data and finding the trending hashtags. Right? MapReduce kind of system. Okay, I'm going through the questions. Can sharding be spread across multiple data centers? Yes, it can be. Metadata for lookup of a photo object will be done by specific one how it is stored on the column. Metadata for lookup of a photo object. So we are storing the metadata, right? So what metadata will have? Metadata will have the photo ID and it will have the photo URL. Let's not say photo URL. Let's say it's photo location. Right. So this is stored in the metadata. So user says that I want to download photo number 123. So the request goes here. Our system finds that okay, for photo ID 123, location is A/B/C. Right, that is on our internal data storage. Right. So that location is the signed URL to this location /A/B/C is provided to the user 123, and then it establishes that connection with the storage layer directly. Okay, coming from the top questions, I'm checking from the top. Geolocation caching CDN stack should be just okay. We discussed this already, Asim, right? I hope it's clear now. It was a good question. Thank you for asking it. Srinivasan, is it possible to provide geolocation storage to reduce the latency? Thank you, Srinivasan, for this question. We have discussed it. Asim, is there going to be a specific discussion about how to solve? Yeah, we have discussed this. Venkata, the question here is where do we compression technique and encryption both are important factors for storing? Yes. So Venkata, so the compression can be embedded in this flow itself. If we go to the high level design. So when the requests are coming to the upload service, right? So what the browser or the client. So we remember, right? We have a signed URL for upload. Right? So in this case, what we can do is that our browser or the mobile client, app client that we have, it in that only we can have the gzip compression parameter added. Right? So if you look at so like HTTP supports this gzip compression, right? So when we establish the HTTP connection and start sending the data, let's say data is implicitly compressed and sent to the signed URL. And similarly, when it is downloaded at that time also, it could be sent as the compressed data, and the responsibility is on the browser or the client to decompress or uncompress that gzip file. Hope that is clear now. Okay, we have talked about the cache. Can it be a hybrid design with popular photos in cache and restaurant storage? Absolutely, Bharat. So that's the core logic of having the caching. The popular photos are sought from the cache and rest of them from the storage. Okay, Amay's question about CDN. So if we need to add CDN here for the download part, so if the user download, it will go to CDN first, and if it's not in CDN, then it will go from object storage. So my understanding, photo in smaller size files, keep per model. Videos and that should be push modes and correct. Yeah, so generally the requests are first sent to CDN to check if the requested object is on CDN or not. And so actually the requests go through CDN. So CDNs are very smart. And CDNs companies are earning a lot of money. They have a lot of intelligence built in now. So actually the companies like Hotstar and these things, they are built right on the top of CDNs. So the request first goes to CDN, then CDN checks if it is available in its cache or not. If it is, then straight away it is served. If it is not there, then it makes call to the backend, and then it maintains it in the cache. And that caching strategy could be LRU or LFU depending on the use case. Right, so videos and others should be push models. Yeah, so even for videos and these things also, the CDNs are used. Like yesterday, Money Heist was released. If Netflix does not serve it from CDNs, they cannot handle the crazy traffic. Similarly, the live matches, they are also telecasted in chunks and stored in CDN, and from CDN those chunks are given to everybody who's watching the live match. That's why there is a bit of delay from the actual action happening on the ground to the time we are watching it. Is there any discussion of query schema design we discussed? Sorting was not clear to me, Asim. If you can add more details. Can you explain again why the photo ID read service was synchronous and not asynchronous? Because you want to get the response in real time, right? Where did it go? Here. Yeah. Right. So you say that I want to see a specific photo. Right. You say I want to see a specific photo. So you expect the response to be sent in 200 to 300 milliseconds, right? So that's why you keep this HTTP connection open, and on that HTTP connection itself, the response is sent by backend to the client, to the user. If you go with asynchronous approach, that means essentially user's request is pushed onto some queue. And when queues come into the play, you cannot have predictable guarantees on the round trip times and the latencies. You cannot have that predictable guarantees. Right? So that's why you need this synchronous. Sync calls are usually create a queue at the client interface. Not sure, Asim, what I saying. Sync calls are usually create a queue at the client interface. Maybe let's just check if in chat box anything is there. Yes, Asim, please give me a minute. Just let me check if there are any remaining questions or items in chat. Garvi is not in foundational video. Thank you. My questions are talking about how to explain on traffic. Yeah, so question is why do we under provision resources at 40% if you have auto scaling option? Good question, Asim, very good question. Because auto scaling takes time to trigger. So if you look at the not sure where the slide is, but for the auto scaling to kick in, we generally have some thresholds. Like if the CPU utilization is more than 60% for maybe 5 minutes or 2 minutes, or if the number of requests have increased by more than 2x for last 5 minutes. So there is a delta here, right? Before which it is detected that auto scaling needs to be kicked in. Second, even when the auto scaling is triggered, it means you have to provision some servers. Right? In old days, when you had to provision virtual machines, it used to take a lot of time. So you provision virtual machine, then you deploy the new service on it, then you wait for the binary to establish all the database connections. You remember there is a step for the service discovery also, right? So there is a delta, a definite delta there. And even today, in case where we have Docker and Kubernetes, so we have brought down the time for the provisioning of the servers, but still that time is still the time matters, because even with Kubernetes, Docker, and all the services kicking it could take few seconds, and it means for few seconds Instagram is down, for few seconds Twitter is down, Google is down, right? So you cannot you cannot go in that situation. Okay, any other questions? I will allow Asim to speak. Asim, please go ahead.
Hi, thank you very much for allowing me to speak. No, I was maybe I'm mixing up, but I mean.
Sorry. Can you please say it again? My volume was low.
Yeah, I'm saying I'm sorry. Maybe I'm confusing it with some other concept, but like when I studied, I'm referring mostly to the concept of synchronous and asynchronous from my from supporting Kafka subsystems, where the concept of synchronous calls means that the call or request needs to complete the full life cycle before any consecutive request to get initiated. So it has to complete the full cycle and of acknowledgement from the server side, and then initiate the second call. So the calls would basically, let's say in case of consumer threads, they will queue up, right, until the first request is completed and acknowledged, right? And that can cause a slow up if you have a lot of traffic coming inbound at the client side. So the approach of asynchronous would kind of speed up the process, but then it's a trade-off. Like, do you really want a real acknowledgement, or you want to introduce parallelism or speed up the transaction workflow? So when you mentioned about asynchronous on read retrieval, I was wondering if there are multiple users, or let's say even a single user, trying to load a reel or something, or let's say a photo something, like a bunch of photos together. Will each of these calls will be wouldn't it be since it's not like a very sensitive type of transaction, wouldn't it be be okay to do a asynchronous call so it can introduce some parallelism on the client side and be loading faster as opposed to a synchronous call?
Yeah, in that case, you will not have asynchronous system. What you will do is that in that case, you will have parallel calls to the backend. Let's say I'll give you an example. Let's say now Instagram has photos and videos both. Right? So let's say and this is the homepage of the user. Okay, so let's say half of the homepage you show photos and half of the homepage you show videos. And let's say there's another feature also where you show some posts also. Right? So this is how the homepage is divided. Now your client, like by client I mean the browser client or the app client, what they can do is that they can send multiple requests, but in parallel. Right? So and they all go to the same backend. Now again, we can have separate services also, where like for photos we have a separate service, for videos we have a separate service, for posts we have a separate service. That is another discussion, but or we can have it on the same server, but we can have the parallel request in this case. Right? And then as soon as they come back with the response, we show it. Now the advantage of this solution would be that, let's say, posts are text based, photos are also lighter, right? So as like till the time video request is getting response, photos and posts start showing on the homepage of the user. And in the background, more videos are also loading, and they do not see the delay. They do not feel the delay. But still, all these are synchronous calls.
Okay, do you think my understanding of synchronous asynchronous is right or is not right, basically?
Yes, your understanding is right. So synchronous is basically when there are two, like generally when your inputs are, when your what should I say? When your input is much higher than the output, or no, or should I say that number of requests are much higher than the capacity of your system. Oh no, sorry, scratch that. Let me see, asynchronous is a completely different. Asynchronous is something when you know that actually I've covered this in prerequisite, but so asynchronous is something when you do not need immediate answer. When you do not need immediate answer, you go for asynchronous call. Right. So what could be the example? Yeah, example is multiple upload. Let's say I'm doing multiple uploads from my system. I'm saying that upload 100 photos. Now, upload 100 photos. Now this can this can go in a queue, this request, and then one by one, though in the background, those photos are just being uploaded. There could be another asynchronous example. Let's say you are on Amazon and you want to download your order history. Where did it go? Now you want to download your order history for last 1 year in a CSV file. Right. Now, Amazon cannot give immediate answer to this question. Download, because it has to go through the 1 year database, find all your relevant orders, then nicely put them in a CSV and send it to you. Okay. So in this case, what will happen is there are two scenarios possible. That so this is definitely async call. In this case, what will happen is that you choose the option that for 2020 download all orders. Right. So in this case, what Amazon will give you a link here, a callback link. And it will say that after 30 seconds or after few seconds, try this link. After 30 seconds, try this link. After 30 seconds, you hit this URL. And then goes a fresh call to the Amazon that, hey, this particular request response is ready or not. In which if it is not ready, then you will get the response, please wait another 30 seconds, right? And you can do that you can do that manual retry, or client can be smart and client can do that automatic retry for you. It can have this kind of icon where it is just retrying it again and again. Or second thing is that you can have WebSockets here, or you can have long polling here. And whenever the data has been processed and CSV file is ready, your client gets a response that your data is ready and downloadable. And you have this on this WebSocket or long polling connection, you get that response. I hope it is clear now.
I think I can correlate, because when you're trying to push, or let's say in this case you are pulling photos, right? When you're doing a download, so it appears like download service has to be synchronous, but upload can be asynchronous, and that will be the faster way to do it, right?
Yes. Yes,
and I was reading the same context in one of the Kafka books, and they were explaining the concept of asynchronous and synchronous. And the whole idea is that if you're trying to retrieve messages from a queue, if you're trying to push messages to a queue, then synchronous is expensive as opposed to asynchronous. So I think it kind of correlate in the context of pub/sub queues, or let's say a queues instance. I was reading a particular section on asynchronous and asynchronous. The idea was, if you're trying to send a message to a message queue, the synchronous calls can be expensive. as opposed to asynchronous. So I think it kind of relates the same way, because here we are talking about the download service, and you're saying the synchronous.
But there has to be a synchronous call somewhere, right? So even if you have a queue, right, and this is the user who is sending the request to the queue, right? So that means you are doing the pub operation, the publish operation. So even doing that publish operation, it has to be a synchronous call. But it could be a very, very small duration call. Because what you are doing is that you are just sending a message to this queue, and this queue says, okay, I have taken this message, and it will just say, okay.
So can you just read the reference I've written in the Q&A? I quoted that excerpt. That's it. So you can see that it says that if you send messages synchronous.
I will have to get more references for this.
Yeah, I can share with you, and maybe we can discuss later.
Sure.
You know, yeah,
Sure.
I have been asked these type of questions earlier also, so this topic is a little bit. I will share, if you allow me, I will share you the reference.
Sure. Please do send me.
Okay.
And this is my email ID. Send it here. Okay, what topic are you teaching next and when? I think I'm planning for either of the two, maybe the sharding, that how we do sharding, and or the Cassandra deep dive. These two are on top of my mind. Okay. Anything else? Or it would be very late for everyone now. I see no further questions, no further chats. Thank you so much, everyone, for your time and patience. And yeah, just as I mentioned earlier, please do make use of all the mock interviews. They are really gold. And practice a lot. There is a lot of useful resources on IK. Go through the fundamental videos by the prerequisites which I mentioned. They will really help you. Yeah, and I see any question. Thank you so much. Okay, thank you so much, Gustavo. Thank you, everyone. I hope you had
Thank
a
you,
good
sir.
time.
Appreciate it.
Bye.
Bye.
Thank you. All the best.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your 3 webinar slot today.